Okay, so now we're going to do two-way ANOVA. So what I mean by two-way ANOVA is before we had a response variable with a single categorical predictor. Now we're going to have a response variable with two categorical predictors. So the first one we're going to do is we're going to say, what if I have these two predictors but only have one observation per each cell? And by cell I mean combination of the treatment levels. So it might be that treatment with the happiness would be pet, and then another one might be gender. And maybe for each pet gender observation I only have one observation. So maybe there is only one statistician with a cat who's female. Or maybe only one statistician who has a rabbit who is male. So in that case, I don't have any replication. So that means I'm constrained. I can't actually get interaction between these two predictors. So here's our two-way layout. We've got our y, I, j. And now this time, I is the level of the first predictor and j is the level of the second predictor. So we have an overall mean plus the extra bit for our first predictor, the extra bit for our second predictor, plus our noise term. And our noise term, we'll again assume, is IID normal, mean of 0, variance of sigma squared. Again, if I try and write the design matrix of that, I will end up with linear dependent columns in my design matrix, so I have to add in some extra constraints. There's two ways you can do it. We've seen the one before. We have the reference category where I'd set the reference level for the first level of the first predictor to 0 and the reference level of the first level for the second predictor equal to 0. That's the way R does it. You can occasionally in R force it to do what we call zero-sum constraints. You'll see some textbooks they use zero-sum constraints. The reason this is here is the zero-sum constraints makes the mathematics easier, but this one, the second one, makes the interpretation easier. And in this case, what we're really interested in is basically our first hypothesis is there what we call a main effect of the first predictor? That is there some sort of significant effect of the different levels on the first predictor? And then one we could ask about the second predictor. So there's two hypotheses of interest. Here is the setup of the model in the zero sum. The main thing you should remember is that the last level can be equal to the negative of the previous levels. And you can see the setup we've got here. You find that generally you have the first level of the first predictor is 1, and then you have this 1 here. But then by the time you get to the last ones, you get a lot of minus ones. I don't use this one a lot. I find it hard to interpret. Here's one we're used to. This time we have that, here's our level of intercepts. This whole first block is all about describing the first predictor, and this is all about describing the second predictor. And basically you get, for example here, you would get a 1 if you were at level 2 of the first predictor or 0 elsewhere. Here's our ANOVA, and what we do is we get our row effects. So this is all about how much your means for the ith, so for the first predictor, change from the overall. You have your column effects, which is how your means of your second level vary. You have your residuals, which is the stuff left over, and the total. And you can do two hypothesis tests. One, you could take the mean square error. So the mean square error here is I take the sum of squares and I divide it by the degrees of freedom. To get the mean square error for B, I take the sum of squares and divide it by degrees of freedom. And again, we see that nice relationship. Here, I said, how many of these sample means are there? There are I of them, minus, there's one overall mean, 1. This one. How many sample means are there? There's j minus 1. You go, well, it doesn't work here now, Jono, but it does, because here you've got how many of these? You've got ij minus I means minus j means plus 1. If you expanded this, you'd get ij minus I minus j plus 1. It matches. And finally, your ij minus 1, ij minus 1. The other thing, and I don't know if I mentioned it last time, is if you add up all the first 3 rows, you'll always get the last one. So here's the F value for testing for an effect of the first predictor, and here's for the second predictor. What if I have replication? What if I have more observations? Let's say there's more than one statistician that's male that has a rabbit. Now I can have an interaction term. Perhaps these two predictors have an interaction effect. Maybe the happiness of a rabbit is more if you're male compared with female or vice versa. So now I can add this to my model. So the I is the level of the first predictor, the J is the level of the second predictor, but now I've got this interaction term, which I've denoted by gamma, IJ, but I've got extra replication. I can now put a K in here, which is the observation within that cell, within that set or treatment level or set of predictors. Now we need lots of constraints to make sure that it's identifiable. So here's how you could do it with the zero sum, and here how you could do it with the reference category. I'm not going to show you the design metrics, they get huge. But now we have an extra column here. This one now is my interaction. Here's my residual. Check that these match what I've said before, but now I have 3 tests I can do. I can test if there's a significant interaction, a significant effect of the second predictor, a significant effect of the first predictor. The usual approach that we do is we always start by looking at the interaction term first. If that is not significant, we refit the model with just the main effects. So we always do interaction first before we look at this. Don't really bother with this F-test until you've looked at this one. If you find that there is a significant interaction term, even if these tests are not significant, because of the principle of marginality, you must keep them in. That's all for now. See you next time.